Shell sort. Shell sort is a comparison based sorting algorithm that is a generalization of insertion sort. The key idea here is to first sort the elements that are placed at interval of a gap, and once you complete this sorting, you'll slowly start reducing this gap till the gap reaches 1. Whenever the gap reaches 1 and you complete that set of sorting, you will have a completely sorted array. This is the logic we are going to use in shell sort. Then there is this question of why can't you simply do insertion sort? Why do you want to introduce this concept of gap in between and complicate things? The reason is there is a speciality of insertion sort that helps us to reduce the time taken whenever you do this gap concept. The speciality is that in case of insertion sort, whenever you provide data that is already sorted or let us say almost sorted, in both these cases, insertion sort runs at order of n time. We know actual time complexity, worst case time complexity of insertion sort is order of n square. But whenever the input data is already sorted or whenever input data is almost sorted, then your actual time complexity will be order of n and not order of n square. So what we are going to do with this gap concept is we'll always make sure that in every iteration the data is almost sorted. So because the data is almost sorted, it will be easier to perform insertion sort every time. So in order to do that, we are going to use two logics. One is the logic that I already explained regarding insertion sort, and the second thing is a logic about data that is generally available. Whenever you take any random data, even though you say it is unsorted data, let us say this is unsorted data, it won't be completely unsorted. That is, it won't so happen that every two elements are in wrong order. If every single element is in wrong order, that means your data is in reverse sorted order. Otherwise, it can't happen. So whenever you say it is unsorted data, the actual scenario would be that the whole array would be unsorted, but there will be small sequences which are already sorted. So maybe these two elements, these are in actual sorted order. Somewhere else, maybe these four elements are in actual sorted order. So this will naturally occur in the data. There will be certain sorted sequences. Moreover, it would also be seen that over the array, when you see from one side to the other end, there will be some sort of ordering that is already present. So we are going to make use of all these orderings that are naturally present, and we are going to decrease the time complexity of insertion sort. So let us see how this is done. So the logic is like this. Initially, we have to choose some certain gap. Generally, what we do is we'll take initial gap as n by 2. If n is the total number of elements in your array, you'll take initial gap as n by 2. After that, if this is your array, let us say this is your array, and you want to sort. The process is like this. Your gap is presently n by 2. So you will sort all elements considering a gap of n by 2. So if you are sorting this element, you won't sort this element by comparing with this. Instead, you will consider that only those elements are present in this array which are at a gap of n by 2 from this element. So let us say first element is this. Second element will be somewhere in the middle of the array. Maybe this one is the second element and maybe third element is this. So you will just see whether these three elements are in sorted order. Similarly, you will compare this element with this element. These are n by 2 distances apart. You will see whether these two are in sorted order. Sorted order in the sense you will only compare this element and this element. So then once you find them in sorted order, you are done with this iteration. Similarly, you will do with every element in this array. For all the elements, you will only compare with the elements that are gap distance apart. So in, let us say after 2-3 iterations, what will happen? Let us see what happens after 2-3 iterations. So your gap, you will keep decreasing this. After first iteration, you will make your gap as n by 4. After second iteration, you may make your gap as n by 8 till it becomes 1. So let us say after few iterations in this particular array, your gap is 3 elements. Okay, your gap is equal to 3, which means you have to consider every element which is 3 distance apart. So you will consider this element with this one, this one, this one, this one. So how will you sort this? You will see, you will consider that only these 1, 2, 3, 4 and 5, only these 5 elements are present in the array, and you want to make sure that these 5 elements are in ascending order. So you will arrange those 5 elements in the ascending order. Similarly, you will take this element, this element, this element, this and this, and you will arrange these 5 elements in the ascending order. So you are not comparing elements of the present set with the previous set. All these are independently sorted, and then what happens is when you do this, there will be more and more ordering present in your array. So as this ordering increases, as you keep decreasing your gaps, you will not need as much time as you would generally need with insertion sort, because there will be more and more ordering present in the data. So by the time you decrease it to 1, so ideally when your gap becomes 1, it should be an actual insertion sort that is going on, because your gap is 1 means you will compare every other element in order, which means at this point you should be doing a complete insertion sort, which should, this single step itself should have an order of n square time. But the reality is, because of the ordering that you have maintained by following this gap procedure, by the time you make gap as 1, it will be almost sorted data, and because of that, time of the last step will only be order of n. So this is the logic we are going to use. What we'll do is, we'll take numbers and try to understand it very clearly how shell sort is working. One more thing, in all the sorting algorithms that we learned till this point, we were able to clearly identify how the name came. That is, if it is insertion sort, you know why it is called insertion sort, why it is called shell sort, why it is called merge sort, why it is called bucket sort. But shell sort, you can't find out like that, because the name shell comes from the person who developed this technique. His name was Donald Shell, and from that the name of shell sort came up. Let us see shell sort from numbers. So we'll take a set of numbers and we'll try to sort it using shell sort technique. So we'll take these numbers 42, 70, 12, 30, 24. Let us have some more numbers so that we can consider gap and do it. 17, 88, 51, 33, and let us say 40. This is your complete data set, and you want to sort this using shell sort. Let us see how shell sort works here. So after this example, you should be very clear on how the algorithm is working. Okay, we'll put indices so that it will be easier to identify. This number was 70, right? Okay, we'll put indices for all these numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 0 to 9 means 10 numbers are there. In the first iteration, let us say gap is 5. So generally you take initial gap as n by 2. Here our n is equal to 10 because there are totally 10 elements. So your initial gap will be n by 2, which is 5. So I am considering a gap of 5. When you are considering gap of 5, which elements do you want to sort? While you are sorting, you want to consider elements that are present at gap of 5. So what I'll do is I'll write those numbers outside the array. I'm doing this for illustration. Actual sorting happens inside the array only, so that you understand clearly which elements we are selecting. I'm going to pick those elements outside and write. So first element, considering 42, and what should be the other element at gap 5 is 17. So this is at 0, 17 is at 5. So 42 and 17 are the elements which are 5 distant. So you have to sort 42 and 17, which means it will be 17, 42. This will be the order because it was not in right order. What you will do, you will correct this. This insertion sort is what you will apply on this. Using insertion sort technique, you will sort it. 17 and 42 is the order. So you will change this to 17, 42. That is done. Next two elements are 70, Which element is at gap of 5 from 70? 88 is at a gap of 5 from 70. If you see 70 and 88, they are already in order. So this is what I'm talking about. When you do this process, you'll understand that there is some sort of order that is already present in the data. Here you don't have to do anything, right? It is already sorted, 70 and 88. Next set is 12 and 51. If you see 12 and 51, again, they are in sorted order. You don't have to do anything. Next set is 30 and 33. What about this? 30 and 33 are also sorted. So again, you don't have to do anything. What is the next set? 24, and which is 5 gaps apart? 40. 24 and 40. Again, these are 5 distant apart and it is sorted. There is nothing to be done. So you are done with this much. So one iteration is completed. You did complete iteration for gap 5. So in the present array, all the elements which are at gap 5 are in sorted order. Next thing is you have to decrease gap to whatever is the present gap's half. So 5 should be decreased to 5 by 2. So you will decrease it to 2. So the new gap is 2. At gap 2 apart, what are the numbers? If you consider from 17, what are the numbers 2 apart? 17. At 2 distance is 12. Then you have 24. Then you have 88. Then you have 33. These are the elements that are 2 distance apart. Is there any sort of order in this? Yes, it is true that there is some sort of order. For example, if you see 12, 24, 88, these are already sorted. So if you consider like that, you will find that there is some order in this data. So let us try doing insertion sort here. If you check with 12, 12 is to be compared with 17. So 12 comes here, 17 comes here. Then 24. When you compare 24, see 24 is already in sorted order. There is nothing to be done. Again 88, it is already in sorted order. So here in insertion sort procedure, there is nothing to be done for this. Then 33, for 33, you just have to move it one step in this side. 33 will come here, 88 will be here. So by insertion sort, you got these many elements sorted. What will you do? You will write this back. So instead of this 17, you have 12 here. Next is 17, 24, then you have 33 here and 88 here. So you have sorted in gap 2. What is the next set of elements in gap 2? You have to take elements from 70. So 70, next is 30, next is 42, next is 51, and the next is 40. Again, if you see, there is some naturally occurring sequence here. 30, 42, 51 are already sorted. Again, if you try to use insertion sort, initially when you consider 30, 30 has to go to the other side, 30 and 70. Then when you consider 42, you will understand 70 has to be moved here, 42 will come here. When you consider 51, you will see 70 has to be moved here, 51 has to come here. See, again, these are single movements. You have to note that when we are doing insertion sort using this gap algorithm, we don't have to do a lot of movements. We either do 1 or 2 movements or no movements. So this is where the algorithm helps. 40 has to come here. So 40 will come here. So this is my sorted sequence for gap 2 second set. So I'll update it. At this point, 30 should come in. Here 40 should come in. Then next 42 is at right position, 51 is at right position, then it should be 70 here. So this is my sequence at gap 2. What will I do now? I'll again divide gap by 2. So 2 by 2 is 1. My new gap will be 1. So at 1, I'll be doing an actual insertion sort of this array. So at this point, see what happens. You will see that there is a natural order in the data. So let us try this. When you are doing with 30, you will see that 30 is already in correct order. When you are working with 17, you will see that 17 has to be moved one step to this side. This will be 17. This will be 30. 40 is already in right order. You don't have to do anything. 24, you have to move 40 here, 30 here, and 24 here. 42, it is already in right order. 33, yes, you have to do a movement. 42 will come here, 40 will come here, and 33 should be here. Next 51, it is already in right position. 88 is already in right position. What about 70? It has to make one movement. 88 should come here and 70 should come here. So this is how shell sort will work. So in this example, when we illustrate it, I hope it is clear for you that automatically we are making use of the natural order that is present, and with this gap concept we are trying to create more order, and slowly we are trying to apply insertion sort in different stages so that at every stage order is there, so that insertion sort becomes easier. So this is what we are going to do. What we'll do is we'll write the pseudocode and we'll try to understand it clear. So let us write the pseudocode. Then we'll see time and space complexities, and that will give us more understanding of the algorithm. So in pseudocode, what should we write? First thing is we should have a gap. A gap should be used. Then we have to keep decreasing this gap till 1. While this, what should we do each time? Each time you should run insertion sort of all the elements which are present at this, whatever be the gap value. This is what we are going to do in pseudocode. So we are going to apply shell sort on array of size n. This is what we are going to do. On array of size n, you want to do shell sort. What is the first thing you have to do? You have to identify gap. So I'll call it G. My gap G is n by 2. So I am putting 2 division signs here so as to show it is integer division. So if n is 9, if you divide by 2, it will be 4.5, but here you will only consider 4. Okay. So gap is n by 2. After this, what should you do? You should run a loop which will run till the point gap becomes 0. So the gap becomes 1. So while what should be the condition? Your gap should be greater than 0. So whenever it becomes 0, you are done. Till the point gap becomes 1, you should keep continuing this loop. So inside this loop, what is it that you are supposed to do? You have to do insertion sort of elements by considering the gap. So how will you do that? First of all, you have to take I'll write a for loop for this. I'll go from gap till the end of array. So how will insertion sort work? Whatever be your present point, from there you have to move till the end of array. For all the elements you have to work. So one thing you have to note here is, when we did the illustration, what we did is, initially we considered all elements that are in a gap. Then we considered next set of elements that are in the same gap. Then we considered next set of elements that are in the same gap. This is how we did when we were illustrating. But in practice, when we are writing algorithm, what we'll do is, we'll go through all the elements at once. And when we are going through the elements, we'll do insertion sort by considering gap. That is, instead of considering every previous element, we'll be considering elements at a gap. So in that way, in single go, we can complete for all the elements, right? So let us say for I is equal to gap. So G is my gap 2 till the end of array. Why am I starting at this point G? Because of the reason that we are considering elements at a gap. Before this point, only one element will be there. And whenever there is only one element is by default sorted. So in insertion sort, we'll consider one side as unsorted, other side as sorted. So one element will by default go into the sorted side. So we don't have to sort it again. So that is why I'm starting from gap till n minus 1. What should I do in this? Let us say I'll keep on some temp variable. Temp is equal to array of I. Whatever is that position, I'll take it. What will I do then? I have to have another loop which will do insertion sort. What should that loop do? That is, considering I selected this element, in all the previous elements, this is the sorted part of array. What will I do? I'll check each element and see whether that element is greater than this element. If it is greater, I'll move it one step ahead. So in shell sort, instead of wherever I said one step, you want to do gap steps. So instead of one step ahead, this will go gap steps ahead. Here, instead of looking into each element, you look into elements which are gap distance apart, right? That is the only difference. What will we do now? We'll have a variable j, let us say j is equal to I. So I'm going to iterate using this j. While, what should be the condition? In insertion sort, you have the condition that this should not go lower than the value of array. So before the gap, we know there is only one element. So j greater than or equal to gap. And what should be the second condition? The value in the previous position, if it is larger than whatever is the present position, then you have to shift it. So array of j minus gap. If this is greater than temp. If this is greater than temp, what should I do? If this is greater than temp, I have to shift the previous element forward. That is what you do in insertion sort. So, okay. So I'll be shifting previous element forward. How will I shift it forward? In this AR of j is equal to array of j minus gap. So here I'm shifting this element forward. So why am I shifting forward? So as to make place for this element, right? Then what should I do? I should do j is equal to j minus gap. So instead of doing j minus 1 in insertion sort, here I'll be doing j minus gap. So whenever I'm done with this particular loop, what happens? Already the right place will be made. That's it. If it is normal insertion sort, what happens? You are starting from this element. This loop will move all the elements which are greater than this one step towards right, and it will make a place for this element to be inserted. Then you have to insert this element there. So presently everything is same, other than that wherever we used 1 in insertion sort, we'll be using gap here, right? So the next step is I have to substitute array of j. Whatever is this, I have to put the value of this one, whatever is the element under consideration, temp. After this, what is the next step? I'm done with this particular loop. After that, I have to decrease gap. My gap will be whatever is the previous gap divided by 2. So again, 2 times I'm writing division sign so that it is integer division. Okay. So whenever this is done, you can return. So return array. Let us once more go through this algorithm and understand. This is the shell sort algorithm. What is this doing? Initially, it is having a gap. It is creating a gap which is initially n by 2, where n is the total length of your array. Then you will start a loop in which you have to loop till the point gap is 1 or more. Because if gap is 0, you are done. When till the point gap is 1, you have to keep applying insertion sort by looking interval of gap. So that is why this while loop is there. What are you doing inside that? For each value of gap, you are going inside the array and going through all elements from gap till the end of array. What are you doing? You are going to apply insertion sort on all those by skipping by distance of gap instead of skipping by 1. Okay. So you will store whatever is the element at I. Then this is the same insertion sort algorithm with the only modification that you will be skipping the distances by gap instead of looking into each element. So whenever the index j is greater than the gap and you are checking whether the elements that you are checking for, are they greater than the element to be inserted. If it is not greater, you don't have to move. If it is greater, you have to move it to the right so as to make space for this element to be inserted, because this element is smaller than that. So it has to be inserted before that. That is why you are having this condition. Whenever this condition satisfies, what will you do? You will move the element one step towards right. So the previous element is moved towards right. So generally the step is 1. Here our step is G. What happens then? You will go to the next element. Next element means previous element in the sorted array. So here previous element means you have to jump by distance G. That is why we are doing J minus G. What is the next thing? Next thing is, once you come out of this loop, you already know the position to be inserted. To that position, you are going to insert temp. So what is temp? Temp is the element you are considering, AR of I. After that, this loop is completed, which means for present gap, your for loop is completed. Whenever that is completed, you will decrease the gap to whatever was the previous gap's half. So you will do gap by 2. and again continue the same procedure. So you will do this till the point gap is 1 or more. So whenever it becomes 1, that is the last iteration, and then when you divide by 2 it will become 0, it will come out of the loop. So this is the shell sort algorithm. Let us understand time and space complexities and what are the specialities of this. So first thing you want to understand here is, in case of shell sort, it overcomes the limitation of insertion sort. What is the limitation of insertion sort? That is, on large data set, if you do insertion sort, what happens? Sometimes you may have to move element through very large distances, which actually contributes to the order of n square time complexity. Here what are you doing? You are making use of the natural order, and you are slowly instilling some order into the data by sorting the value in gaps. Because of that, you are decreasing the time used for insertion sort. Another thing is, see, this is a simple to implement algorithm, does not require any additional space, and generally it performs better on nearly sorted data. We know insertion sort performs better on nearly sorted data. Here you are adding more of that unity or order. So because of the order, it will perform better than insertion sort. Next thing is, what are the time and space complexities? So coming to time complexity, first thing is, if you ask what is the worst case time complexity, is order of n square only. So worst case time complexity, we know for insertion sort it is order of n square. For shell sort also it is order of n square. But the point is, shell sort has an average case time complexity of order of n log n. So this is why shell sort is interesting. So mostly when you use shell sort, you will be hitting the average case time complexity, which is order of n log n. So technically, theoretically, if you ask what is the worst case, it is order of n square. But the interesting part about shell sort is, mostly shell sort will hit only order of n log n. So this is the average case time complexity. Next thing is, it is n log n. Next thing is about space complexity. What about space complexity? We are not using any extra space here. So space complexity is order of 1. See, there is constant extra space for variables, but other than that, nothing. So space complexity is order of 1. Time complexity is order of n square in worst case, but average case is order of n log n for shell sort. So, and one more thing, is it stable and in place? First of all, it is in place algorithm because all the modifications are done on the input array only. You are not using any other data or any other data structures in order to do modifications. Whatever insertion sort you are applying, everything is applied directly on the given input array, which means it is an in place algorithm. This is a in place algorithm. Next question is it stable? You know, insertion sort is already stable. So does that mean shell sort is also stable? This is the question. So we know insertion sort is stable, but shell sort is not stable. The reason for its instability is that we are doing this gap process. Because of gap process, there may be swappings beyond elements which are of equal value. Because of this, maybe there is one element here of one value, one element here which is also of same value. This element may be swapped with this element because of the gap procedure. If it was going one step like insertion sort, it would not have swapped with this element because both are same values. But because this is having gap procedure, this may get swapped with some other elements which will disturb the order. So the actual order of equal valued elements may be disturbed in the sorted array, and because of that reason, it is not stable. So it is in place and not stable.